Okay, let's talk about regulation of breathing. I think this is kind of fun, so I hope you do too. Certainly interesting. So how do we breathe? What causes us to want to breathe? Well, there are the central chemoreceptors. They are in the CNS. They are in the medulla oblongata. And the central chemoreceptors in the CNS account for about 70% of the drive that tells yourself to breathe. And the central chemoreceptors in the medulla, they work by monitoring the pH of the CSF. And you know that carbon dioxide levels affect pH through the reaction that we've been doing numerous times. Okay, so the pH changes in the blood with the carbon dioxide, but the ions that are produced from the acid cannot cross the blood-brain barrier. They're charged. Remember that the blood-brain barrier is selectively permeable. Small stuff cannot just pass through like it can at the systemic capillaries. So the hydrogen ions can't get into the CSF. They stay in the blood and are buffered there. But the carbon dioxide that is floating around in the blood can cross the blood-brain barrier. It diffuses across, simple passive diffusion, and gets converted to carbonic acid through that same reaction that we've looked at. Now this is in the CSF, so this is in CSF, and the CSF has little buffering capacity in it. There's not a lot of protein. So the pH changes rather quickly in the CSF, and that's what the central chemoreceptors detect and respond to. So let's take a look at the next slide. Here's a neat little graphic. The central, or the cerebral capillary rather. So this is in the brain, and there's our blood-brain barrier represented by just a solid line. Again, the hydrogen ions cannot diffuse through. They have to stay in the blood. Yellow doesn't really show up, but the carbon dioxide can. And in these figures, the yellow egg-like oval is a stimulus or a stimulatory signal. So that does diffuse into the CSF, cerebral spinal fluid. And then it goes through the same reaction that we've looked at before. So just follow this through, make sense out of it. Carbon dioxide plus the water, back and forth. It's a reversible reaction. There's the enzyme, carbonic anhydrase, makes carbonic acid, and then the hydrogens dissociate. All right, we're in the CSF. Now the pH is changing. There's very little buffering. And the hydrogen ions and some of the carbon dioxide, they stimulate these central chemoreceptors. And then that signals these respiratory control centers that are in the medulla oblongata, and then that just leads to increased ventilation. Pretty straightforward. It's kind of neat. So you should be able to describe the effectors that produce increased ventilation. So how do we increase ventilation? How do we get more air in and out of the lungs? Well, you have to expand and contract the rib cage to do that. So the effectors are those respiratory muscles. These are all skeletal muscles, of course. We're not talking smooth muscle. So respiratory muscles, MM abbreviated for muscles, plural. So you should name them again for review. That's what's ventilating the lungs. So those are the central chemoreceptors, about 70% of the drive. So, a little bit more. We talked about the central chemoreceptors. This is a note on the peripheral chemoreceptors. And they are out in the carotid, in the peripheral nervous system. They're in the carotid and aortic bodies in the same place as the baroreceptors were. Carotid sinus and embedded in the aorta. And these peripheral chemoreceptors, part of the PNS, peripheral nervous system, account for about 30% of the drive. So the central are 70, the peripheral are about 30. And the peripheral chemoreceptors monitor primarily oxygen. It was the central chemoreceptors that monitored pH and CO2. So the peripheral chemoreceptors, though, only become stimulatory, they only really kick in when the oxygen level and the PO2 drops below about 60 millimeters of mercury. And this is quite low. Okay, so if this oxygen level drops below about 60, then these peripheral chemoreceptors kick in. And with COPD, and which produces, patients with COPD have a chronic hypercapnia, and hypercapnia just means elevated CO2 in the blood. So we do two up arrows for elevated CO2 in blood. They're retaining the CO2. They're not getting rid of it at the lungs. It's an obstructive pulmonary disease. They're unable to ventilate the lungs adequately. Okay, so under these conditions, the chemoreceptors, remember those are the ones back in the CNS that are being stimulated by low pH. So with chronic hypercapnia, excess CO2 in the blood, excess CO2 in the CSF, more acid, lower pH, the chemoreceptors are active. But if this goes on for a long time, those central chemoreceptors become habituated and they reset. Stop that maybe more buffer gets pumped into the CSF. So we have elevated CO2, right, from COPD. It's in the CSF for a prolonged period of time, and those central chemoreceptors sort of shut down. They become habituated. They're no longer stimulated. So they're no longer providing the drive. Remember, they're accounting for 70% of the drive. Well, they are shut down and turned off. Well, with COPD, as the CO2 level goes up, the oxygen level is typically going down also. So with CO2, they can't get the oxygen in the blood, and it then drops below 60 millimeters of mercury. So now those peripheral chemoreceptors kick in, take over, and provide what's referred to as a hypoxic drive. This is the drive to breathe. And the drive to breathe is being stimulated by low oxygen, hypoxia. So that's the hypoxic drive being produced by the peripheral chemoreceptors. Okay. So play with that, the role of the central and the peripheral. Let's take a look at the last slide, and then I'm going to talk about shallow water drownings. So before I do that, let's just finish up this slide. And it's just another way of organizing the information and presenting it in what's often described as a concept map. So again, the little yellow oblongs are representing a stimulus in this flow chart. Remember, this is just concepts. So it's sort of like an engineer's flow chart. We'll just make all little yellow oblongs a stimulus. So it's summarizing what we had talked about with the central and the peripheral chemoreceptors. So increased CO2 level in the blood. Well, we talked about how that diffuses across the blood-brain barrier and into the CSF. So we're just reviewing what we already talked about. In the CSF, it gets converted to carbonic acid that then dissociates the hydrogen ion, and that stimulates central chemoreceptors, which then stimulates ventilation, which we talked about. So that's just another way of presenting it. The peripheral chemoreceptors are stimulated primarily by, let's just stick with the carbon dioxide. Remember that this is about 70% of the story, central chemoreceptors, and the peripheral chemoreceptors are about 30% of the story. So they also respond to carbon dioxide and pH, but not to the same extent in the plasma. Okay, so low oxygen. If it drops below 60%, what this figure is showing is that drop, that low oxygen, then stimulates the peripheral chemoreceptors and we increase ventilation. And that was our hypoxic drive. And then this is just showing sort of classic negative feedback. So when the oxygen level increases, this stimulus gets shut off, and when the CO2 level decreases because we're ventilating the lungs, that slows down the upper pathway also. Oh, and I put a note here. What about higher brain centers? So we're talking about regulation of breathing. We've talked about central chemoreceptors, peripheral chemoreceptors. What else regulates breathing? Well, higher brain centers, such as we talked about before, maybe fear, anxiety. Some people with anxiety have sort of a breathing, an anxiety attack. They start to hyperventilate. On the flip side, relaxation, calm, deep breathing. You can voluntarily affect your breathing rate. Also, proprioceptors, again. We talked about these with the cardiovascular system. Once the body starts to move and be active, those proprioceptors in the joints, tendons, ligaments feed signals up to the brain. The brain realizes, oh, the body's moving. Let's crank up the cardiovascular system. Let's crank up the respiratory system to keep up with it. So, the last topic that I want to talk about, I don't have a slide for this, so take some notes. This is the idea of shallow water drownings. Near and dear to my own heart. My friend and I when we were kids, were almost victims of this. So this is how it works. This happens frequently, not often, but often enough, I should say, where people are in shallow water and they drown. And it often occurs, most of the time, from trying to hold their breath. And my friend and I, when, I don't know how old I was, maybe 10, we're in the swimming pool late at night, and it's an Olympic-sized pool. We're down at the shallow end, and we want to play frogman, and we want to swim all the way underwater of this Olympic-sized pool from the shallow end down to the deep end. That was exciting. So we would hyperventilate like crazy. And we completely overdid it. We were down there hyperventilating. I don't know, I think, hang on, I can't write and talk at the same time. Hyperventilate. So I think we were doing it probably for 5 minutes, watching the clock, waist deep water, huffing and puffing as hard as we could, deep breath in, deep breath out, and then we would dunk under the water and swim the length of the pool, no problem, without coming to the surface. To the other end. And we did that. We did it quite a few times. Well, what was happening? What's the danger in this? Well, as a 10-year-old kid, we thought that when we were hyperventilating, we were increasing the oxygen level in our blood. That made sense in our mind, but that wasn't the case. That's not what was going on. Because remember, from our oxygen hemoglobin saturation curve, that at normal alveolar PO2, which we were, the hemoglobin was already 98% saturated with oxygen. So hyperventilating is not going to increase the amount of oxygen in the blood. The most we could get would be about another 2%. But that doesn't happen. You have to get the partial pressure up to about 600 millimeters of mercury before you hit 100% saturation. So we were not adding oxygen to our hemoglobin. So what were we doing? And why were we able to swim underwater and hold our breath without this overriding desire to come to the surface and take a breath, which is the normal response? Well, we were hyperventilating and we were blowing off the CO2. So we're blowing off the CO2. There's less CO2 in the CSF. So there's less acid and less hydrogen, which leads to less stimulation of the central chemoreceptors. Remember, that's 70% of our drive. Well, we just turned them off. Central chemoreceptors. That's what was going on. So we just reduced our drive, the drive to breathe. I mean, we knew that because we didn't have the urge to come up and take a breath. We just figured we were running on all this extra oxygen that we had. Well, meanwhile, what's happening? The CO2 levels are starting to build up, but we can get down to the end before they get high enough to cause us to want to take a breath. So the central chemoreceptors are out of the picture. Our drive is out of the picture. There's no drive. Meanwhile, what's happening to the oxygen level? So the oxygen level, we start out at 98% saturated. Well, as we're swimming underwater, the oxygen level is going down. It's getting lower and lower and lower. Unfortunately, we got to the other end of the pool and popped up. But if we hadn't, if we had kept going and you get below a certain level, then you just black out. The brain shuts off. If you reduce the oxygen level to a certain amount, then the brain is incredibly sensitive. You black out underwater, And when that happens, you don't sort of wake up with a jerk and come up sputtering. No, if you black out underwater, the lights stay out and that's it. Your brain was turned off, it's not going to turn back on. So that's the danger. That's basically what happens with shallow water drownings in this context. So be careful to watch your kids if they get into this holding their breath underwater. I think it's fine, but just watch them and be careful. Okay, so that's it for this lecture. The very last one we'll look at ventilation and perfusion coupling. We'll see you soon. Bye.